Hi, this is lesson 2 of unit 5, which is reaction rate, and in this lesson we'll be talking about Le Chatelier's principle as well as how to calculate the equilibrium. So for our lesson objectives, students will be able to predict the shift in a reversible reaction when there's a change in either concentration, temperature, or pressure. Also, students will learn how to calculate the equilibrium constant for a chemical reaction. Let's start with Le Chatelier's principle. Le Chatelier's principle states that if stress is applied to a system at equilibrium, the system shifts in the direction that relieves the equilibrium. So for example, if you change the pressure, it might shift from the reactant to product or backwards. If you change the temperature, it might shift from product back to reactant or backwards, whether you're heating it or cooling it. Or also if you change the pressure, it will also have a shift, though sometimes it's possible not to have a shift, and we'll also look at a scenario such as that. So we're going to begin with concentration. Alright, what if we change the concentration? That means we're either going to add more reactant or take away the reactant, or same thing for the product. We can add more product or take away the product. How will that make the reaction? Will it shift to the left or to the right? Alright, if it shifts to the left, you say it shift towards the reactant. If it shifts towards the right, you're saying it can shift towards the product. Alright, so here we go. We have our first reaction right there. It says predict the shift of the reaction if the concentration of the reactants increase, the concentration of the reactants decrease, the concentration of the product are increased, and the concentration of the product are decreased as well. Alright, so let's go ahead and solve for this one. We have this reaction right here. CO, carbon monoxide, plus 3 hydrogens reacts to give you methane plus water vapor. And let's go ahead and rewrite it again. So we have CO plus 3H2. It's going to give you CH4 plus H2O. That's the reaction. So the first question they ask, if the reactants are increased. So what happens if we increase reactant, the concentration of the reactants. If we increase the concentration of the reactants, these are the reactions. A lot of times I ask students to visualize it like this. Picture that here on top of the yield, which I'm going to put 2 arrows because it's a reversible reaction. Picture that having a ball on top. That's usually the visual I would say. Picture that having a ball on top. Now what if I say that the left side, which is the reactant side, we're going to go ahead and increase it. So we're going to lift this up, the left side. Which way would the ball roll? If we were to get the left side and lift it up, what should roll towards the right? So this reaction will shift to the right. On the other hand, what if we get the concentration of the reactant and we decrease it? Alright, so now let's take a look at that. So what if we decrease the concentration of the reactant? Alright, we'll picture that. Again, here's a reaction, and if we pull the reactant side down, either we take away carbon monoxide or we take away hydrogen. If this side goes down, which way would the ball roll? It will roll to the left. This reaction will actually shift towards the left. Alright, now, second part of that. What happens if the products are both increase and decrease? So let's go ahead and take a look at that. So if we increase the concentration of P for product, and we'll also look at what happens if we decrease concentration for the product as well. Alright, so now the products are on the right side of the arrow, which is known as the yield. So for the first one, what happens if we increase it? So we're going to go ahead and raise it up, increase it. Which way will this ball roll if we were to get this side of the reaction, just lift it up? So picture that as if we had a ruler and we are lifting up this side, the ball will roll to the left. So you notice that will be your answer for this one. But what happens if we decrease the concentration of the product? So if we bring it down, again, picture the reaction as being a ruler here, and if we bring this side down, which way would the ball roll? It would say we'll roll towards the right. So that is correct. So those are the answers. If we add more reactant, it's going to go towards the right, and if we take away some reactant, it's going to go to the right as well. So if you really want to get as much product as possible, perhaps you want to collect methane so you can sell it from this reaction, you want to go ahead and add as much of the reactants as possible. So keep adding more carbon monoxide, keep adding more hydrogen, And if you want to again go to the right because you want as much product as possible, as soon as the product is made, you want to go ahead and remove it. And that will make the reaction go towards the right as much as possible, giving you a higher yield. Alright, that takes care of concentration. Now we're going to look at temperature. Now in temperature we look at two scenarios. What happens if you have an endothermic reaction versus an exothermic reaction. So let's go ahead and take a look at the first one. The first one is an exothermic reaction. An exothermic reaction is one where energy is released. So the material gets hotter. Alright, so paper burning would be an exothermic reaction. Alcohol burning would be an exothermic reaction. Alright, so what happens if we raise the temperature for an exothermic reaction? Alright, so I'm going to go ahead and write it down. Sometimes when the reaction is too long, it doesn't fit on a slide. This is what you do. You send it over to the next line. So it looks a little split, looks a little weird, but that's the proper way to do it. When the reaction is a little too long, it does not fit. So you have two hydrogens react with oxygen, and that yields a water molecule plus 200 joules of energy in this chemical reaction. Alright, so keep an eye on that chemical reaction. Let's say that this reaction releases 200 joules of energy. So now the question, hey, it is an exothermic reaction. You can tell because the energy is on the on the product side. The energy is on the product side, so it's on my right hand side. So if we were to heat up this reaction, if we were to get the temperature and increase the temperature. So if we increase the temperature, what would happen to this reaction? Would it shift to the left, to the right? Again, for a reversible reaction, I want you guys to go ahead and picture a ball sitting on top of the yield, and if this were a ruler and the temperature, that's your energy, right? If we were to increase the temperature, so raise up the right side, the ball will roll towards the left. Alright, so that's what would happen. Now, what happens if we decrease the temperature? Alright, so now we're going to go ahead and bring the temperature down. So if we bring it down, we're lowering the temperature, cooling it down. Again, picture that. We're bringing this side down. Which way would the ball roll down the ruler? It will be to the right. So the reaction actually also follows that rule. It will shift towards the right as well. Alright, so that is an exothermic reaction. So now the next one, let's take a look at an endothermic reaction. Endothermic is one that requires energy for it to happen. Alright, so for example, if you ever had a first aid kit that has a cold press in it, you go ahead and instant ice bag, you go ahead and twist it, and inside has a chemical reaction that gets very cold. That's an example of an endothermic reaction. And here we have another endothermic reaction. So we're going to go ahead and then write it down. So for this one, it's going to be 2NaH2PO4 plus 150 kilojoules, and that's going to go ahead and yield Na2H2P2O7 plus water vapor. Alright, so that's the reaction. Now I want to point out this, important to this whole reaction. Notice that the energy here is on the left side. That's the reactant. That's how you know it's an endothermic reaction. It's going to be on the left hand side. Now, we're asked the same questions. What happens if we increase the temperature or decrease the temperature? Let's go ahead and take a look at those. If we increase the temperature versus if we decrease the temperature. Now, what are we going to get? Well, again, picture a ball right there on top of the yield, but the energy now is on the left side. So if we increase the temperature, that's going to be the reactant side is going to increase. The ball, if we're on top of this ruler, since we increase the reactant, it's going to roll to the right. But if we were to decrease the temperature, bring it down, so again, picture that on a ruler, if we're bringing the left side down, that's going to roll to the left. And you'll notice that an exo and endothermic reaction are opposite. They give you opposite answers for these. Alright, so that takes care of concentration and temperature, how it affects it. Now we're going to go ahead and look at pressure. Now pressure is a little bit different. The examples I've been using with my ruler no longer apply for pressure. Pressure is slightly different. Alright, so that's up next. So we're going to look at 3 different reactions for pressure. All right, so here's our first one. It is nitrogen reacting with hydrogen to create ammonium. All right, so for the first one, the rules that you need to know is the following. When you increase the pressure, I'll put arrow pointing up. When you increase the pressure, what will happen is that the reaction will shift from the high number to the low number. We're going to go from high to low. And what I mean by high and low, I mean by how many gas molecules there are. In one of the sides of the molecules, or the reaction is going to have more gases than the other. So when you increase the pressure, it will flow from the high to the low. If you decrease the pressure, it's going to flow from the low number to the high number. So it's going to do the opposite. So you got to count how many gas molecules do I have on the left side and how many gas molecules do I have on the right side. Alright, so that's something you're going to have to do. So let's go ahead and write down the first one for pressure, which is, let's see, N2 plus 3H2 give you 2NH3. That is it. Now, here we have the G in parentheses. What does that mean? It means gas. If you see a G, that's in the gas phase. If you see an L, it's in the liquid phase. If you see an S, it's in the solid phase. This one we have gases. How many gases do we have here? A lot of students will tell me, oh, we have 2. Not quite, we have 4. See, there's no number there, means 1, and there's 3 hydrogens. Total of 4 gases on the left-hand side. I'm going to go ahead and write that down. There are 4 gases here. Alright, on the other side, ammonia is gas, and there's only 2 of them. So, who's our high number, who's our low number? This is our high number, this is our low number. Because 4 is higher than 2. Alright, so that's what we got. Alright, now, what happens if the pressures increase and what happens if the pressures decrease? Alright, so let's go ahead and take a look at that. So we're going to say that the pressure is increased and pressure is decreased. Which way would the reaction shift? To the left or to the right? Alright, so for this one, pressure is increased. If we increase the pressure, it flows from the high to the low. Here's the high, there's the low, so go from high to low, that is towards the right. So that's our answer for if the pressure is increased for this reaction. What happens if the pressure is decreased? Well, the opposite is going to happen. Lower the pressure is going to flow from the low number, which is a 2, over to the high number, which is a 4. Alright, so that's going towards the left. Alright, so that's our first of 3 molecules we're looking at, or reactions we'll be looking at for pressure. The next one is this one, predict the shift. Again, we're going to go ahead and increase and decrease the pressure. So let's go ahead and write this equation down. So we're going to have NH4NO3 ammonium nitrate on the left hand side, NH4NO3, and on the right hand side we have N2O plus 2H2O. Alright, let's count. How many gases do we have on each side? On the left hand side, if I ask you how many gases are there here, a lot of students say there's 1. Well, there's 1 molecule. But notice the S is a solid. So the answer actually is there's none. So I'm going to put down a 0 here. There's no gases on the left. On the right, here we got G and a G, those gas, that's a gas, and there's 2 molecules for the water vapor. And so therefore a total of 3 gases on the right hand side. So this is our low number because 0 is lower than 3. 3 is a high number. Notice how it's opposite from the first example we did where the high was on the left, the low was on the right. This is the opposite. So same question we're going to be asked is what happens if we increase the pressure or decrease the pressure? So let's write those down. Pressure increase. What will happen? Flow to the left or to the right? Pressure decrease. Alright, so now that we have those, let's go ahead and work those out. Alright, if we increase the pressure will flow from high to low. This is our high, that's our low. So it's going to go in that direction, so it's going to go to the left. Now, what happens if we lower the pressure, decrease the pressure, it's going to go from low to high. So from low towards the high, so that is towards the right. And because the high and low are switched, notice that our answers are also switched as well. All right, let's go ahead and move along then to our last problem for pressure. We have here the combustion of methane, and we're asked to predict what happens does it shift to the left or to the right when the pressures increase and when the pressures decrease. So let me go ahead and write that formula down. So it is CH4 plus 2O2, which are both gases, and it's going to be CO2 plus 2H2O. All right, if all of these are gases, and if we count how many gases on the left and how many on the right, there's 2 plus 1 on the left, 2 plus 1 on the right. So this one has 3, and the other side has 3 as well. So which is the high and which is the low? There is no high, there is no low. So therefore, what happens when you raise the temperature, or the pressure, I should say, or when you increase the pressure, decrease the pressure, what happens? The answer is there is no shift. It does not shift towards the right, does not shift towards the left, because there's no high, there is no low, so that's why there is no shift. All right, that takes care of Le-Chatellier's principle. Up next, we're going to go ahead and discuss equilibrium. In a chemical reaction, as the concentration of the reactant decreases, the concentration of the product increases. All right, so for our made-up reaction right there, where A is the reactants turning into B, what's going to go ahead and happen is that the reactant, there's less of it, so that is represented here by the red line. So let me go ahead and label that as A. And the blue line represents our product. I'm going to go ahead and label that as B. So that's what happens. Now, you look at the graph very carefully, you'll notice that for both the red line and the blue line, the very instant they begin, the slope is very, very steep. That means that the reaction goes very quick. But as the reaction continues, the slope is not nearly as steep. Eventually, that slope will flatten out completely so that the lines are parallel to each other. And that is the point where we reach equilibrium. And that way we have more or less constant numbers of reactants and products. Now, in equilibrium is a state in which no net change takes place in a system. In equilibrium, the forward and the reverse reaction rates are equal. So picture this. Let's say that I'm going to go ahead and draw a few molecules here, 3 of them, and those are my reactants. I'm going to put an R on the bottom for a reactant. And now they're going to go ahead and react and turn into the product, which I'm going to put on the right, label it P for product. And let's say we got a total of 5 molecules here. Now, equilibrium occurs when every time one molecule from the left goes to the right, you also have the opposite happen when one molecule from the right goes to the left. So now, since you have the same number of molecules, you end up with the same amount of reactants as you do product. In this case, 3 reactants for every 5 products. So you can say that there's really no change. So that's when they say no net change takes place. That's what they're referring to right there. Now, a misconception that students have is that equilibrium takes place when there's equal numbers of reactant and product. No, that's not the case. In this scenario that is in equilibrium, when you have the same number of molecules going back and forth, notice that for the reactant, we have 3 molecules, and for the product, we had 5. So it's not when you have equal numbers of reactant and product, it's when you have the same number of molecules moving back and forth. So therefore, the overall numbers don't change. Now, equilibrium constant, that is what we're going to be solving for in this lesson. It's a ratio of product concentration divided by the reactant concentration. So the concentration of product you're going to put in the numerator, the concentration of the reactant will go in the denominator, and you go ahead and divide them to get the value for the equilibrium constant. If your answer comes out to be greater than 1, that means that the reaction is product favored, meaning that there's a lot of product and very little reactant. On the other hand, if your KEQ, the equilibrium constant, comes out to be less than 1, that means that the reaction is called a reactant favored reaction. So if it's reactant favored, that means you have a lot more reactant and very little bit of product. What does it mean if it's exactly 1? It is unlikely to get that answer, but what it means is you have equal numbers of reactant and product. Now let's go ahead and solve some examples. In example 1, we're asked to follow In example 1, we're asked to find the equilibrium constant for this reaction. How would you set up this chemical reaction so that we can go ahead and find the KEQ, the equilibrium constant? Well, KEQ is set up as such where the product is on the numerator and the reactant is on the denominator. And remember that the reactant is the left side of the yield, and on the right side of the yield, that is where you find the product. Alright, so let's go ahead and solve this problem. KEQ. Alright, so what's on the right hand side? That's the product. The product's going to go on top. Notice the coefficient in the front is going to go ahead and become an exponent. So I'm going to put that 2 on the top right there. So the number in the front becomes an exponent. Everything else, including the tiny subscript right there, just goes inside the brackets. So it's going to be KClO3. Alright, that takes care of the numerator. On the denominator, notice that it's 2 separate molecules with a plus in between. So I'm going to put 2 sets of brackets for them with a multiplication in between. And you're like, but it's a positive plus. No, it's multiplication when you put it into the equilibrium constant. Alright, what about the numbers in the front, the coefficient? Those becomes exponents, so that's a 2 for the KCl. And for the 3 oxygens, it's to the 3rd power. So you cube that one for the oxygen. And that will be the setup for the equilibrium constant. In the follow-up problems, we're going to go ahead and substitute numbers in. But for right now, we're just setting up the formula. In example 2, we're asked a similar question. Write the equilibrium constant for each of the following. We have A, B, and C. So here are their reactions, and we're going to go ahead and put them into the equilibrium constant. And remember that the product goes on the top, the reactant on the bottom, whereas the reactants on the left-hand side, the product's on the right-hand side of the arrow, which is called the yield. So here we only have 1 molecule, so I'm going to go ahead and put it in brackets. Na2O. And what about the coefficient? Now it goes in the numerator. Now it becomes an exponent. Alright, now here notice that there's 2 separate molecules. I can tell that they're separated by the plus sign. So I'm going to put 2 sets of brackets, multiplication between them. Alright, for Na, so I'm going to put Na in here to the 4th power and O2. There we have it. So that'll be your setup for the first one. Like I said, later on, we're going to go ahead and substitute numbers into it and solve for that. Alright, let's go ahead and solve for this one. Notice that there's 2 separate molecules with a plus in between. Plus in between means I need to put 2 sets of brackets in between them. So carbon is here, and there's a 2 in front of it, a coefficient, so it becomes to the 2nd power, and that's just hydrogen. What about the small subscript? You just put it inside the brackets. On the left side, it's just C2H2. That's it. And for this last one, we got on the product, goes in the numerator, there's a plus right there. So we're going to go ahead and put 2 sets of brackets with multiplication. CO2 will be inside of one of them, and the other one is H2O. And again, what happens to that 2 right here? It's going to be to the 2nd power. Next right here, on the left side, we got positive right there. So that means we're going to separate them. Those are 2 separate molecules. So we're going to have the CH4 on one side, H2O on the other, and notice that there is a 2 in front of the H2O. I'm sorry, the oxygen gas, so we'll put it right there. And that will take care of example number 2. In example 3, we're asked the following question. Calculate the equilibrium constant for this equation. Hydrogen gas plus iodine reacts to form hydrogen iodide. And they give you the concentration for hydrogen iodine and hydrogen iodide right here. Here they are. So we're going to begin by just setting up the problem. So I'm going to go ahead and write down the equilibrium constant. Remember that the product goes on the numerator. So that's going to be HI. And the 2 in the front, the coefficient, becomes to the power of 2. And the denominators, you see that plus separating the 2 molecules. That means I need 2 sets of brackets, multiplication in between. Alright, there's hydrogen gas and I2. Alright, now we have the setup for the formula. We're going to go ahead and substitute the numbers in. Those were given to us right there. So we're going to plug in all those values and then solve for the KEQ. So let's go ahead and do that. In this problem, let's see. HI is 9.0. Substituted to the 2nd power. Notice that once I switch from letters to numbers, I no longer use brackets, I use parentheses. Alright, next is going to be for H2, 0.5, and I2 is 0.4. There we have it. Alright, now we go ahead and we use a calculator and go ahead and solve for this one. So we're going to start by the top exponent. So KEQ, it's going to be 9 squared, that's 81. And then 0.5 times 0.4 is going to give us 0.2. Now, what are we going to do? We're going to go ahead and divide 81 divided by 0.2. It's going to give us an answer of 405. Units for it? There's no units for it. So that's our answer, 405. Now that answer is greater than 1. What does that mean? It means that this reaction is product favored. That means there's a lot more product than there is reactant. Alright, that takes care of example 3. In example 4, they ask you solve for the equilibrium constant for this equation right here, which is sodium reacts with oxygen to give you sodium oxide. And here's the concentration for each one of the reactants and the product. Alright, so now solve for KEQ. We're going to go ahead and set it up. KEQ is equal to, on the numerator you put the reactant, so that is going to be Na2O to the second power. And then the plus means that they're two separate molecules. So I'm going to put two separate sets of brackets. Na, to take one of them, and notice the 4 in the front, that means that it is to the fourth power, and then the O2 right there. Alright, now that we have the setup, we're going to go ahead and plug in all these values here and solve for KEQ. So let's go ahead and begin to plug in. KEQ is equal to, alright, Na2O, it is 0.03 to the second power, and A, it is 0.2 to the fourth power multiplied times 0.1. Alright, at this point what I would usually tell my students is don't try to put it all at once in your calculator. Multiply the top, solve for the bottom, and then divide at the end. So let's get the answer for each of those parts. So 0.03 squared will give us 9 times 10 to the negative 4. And for the denominator, it's going to be 0.2 raised to the fourth power times 0.1. It's going to give us 1.6 times 10 to the fourth power as well. So we go ahead and we divide 9 times 10 to the negative 4 divided by 1.6 times 10 to the negative 4 gives us our answer of 5.625. Again, no units for the answer. What does that mean? It is a number that is over 1. Therefore, again, it's a product favored reaction. That means that there's more product in this reaction than there is reactant. That takes care of example 4. In example 5, we're asked the following question. Solve for the equilibrium constant for this reaction, which is C2H2, and it's decomposing to break down into carbon and hydrogen gas. If they give you guys the following concentrations, as you see right here, for each one of the reactants and products. Alright, so we're going to go ahead and set up the equilibrium constant for this reaction, KQ. Again, the products go on the top. Notice the plus in between them means that you need two separate sets of brackets for them. Alright, so there's carbon and there's a 2 in the front, so you put it on the top. And hydrogen, and you're like, there's a 2 right there. Well, that's a subscript, you just write it in there. You don't really do anything with it. Alright, for the left side, that will be the reactant that goes in the denominator, C2H2 in brackets. Next, we get the numbers and plug them in. So let's go ahead and do that to solve for KEQ. Alright, so that's going to go ahead and be C, it is 0.50 squared multiplied times H, which is 0.90, divided by 0.40. Those are all the values to plug in. Alright, so I'm going to go ahead and solve for the numerator first, and then I'll do the division. So 0.5 squared times 0.9 gives me 0.225 over 0.4. Once I divide that, it gives me the answer of 0.5625. Alright, what does that mean? It means that this value is less than 1, so therefore it is product favored. There is more product, that is less than 1, it is reactant favored. That means that there's more reactant than there is product. That takes care of example 5. In example 6, we're given the following problem. It says, the chemical reaction for iron with sulfuric acid will give you iron 3 sulfate plus hydrogen gas, and has an equilibrium constant, a KEQ, of 133.3. Find the concentration of iron if The sulfuric acid is 0.3, iron 3 sulfate is 2.0 molar, and hydrogen gas is 4.0 molar. As you see right here, there's all the values. Alright, so that's what we're solving for, and this time we're given all the other values, including the KEQ at 133.3. So we're solving for the concentration of the Fe. That is what they want in this problem. So slightly different from the other ones. So let's go ahead and set up as we did before. KEQ is equal to, we're going to put the product on the top. There's a plus in between them, so we're going to put two sets of brackets. One for the Fe2 SO4 parentheses 3, that's iron 3 sulfate, and H2, the hydrogen gas. Alright, on the other side we're going to put Fe multiplied times H2SO4, the sulfuric acid. Alright, now that we have that, what we really want is we want to go ahead and solve for Fe. So how am I going to do that? Well, just like you would do in your math class, we need to get it out of here and isolate it on one side of the equal sign. So I'm going to multiply both sides by Fe. So I'm going to put Fe on this side as well. And these two will cancel each other out. Great. Now we got that. I want to isolate the Fe, so I'm going to go ahead and get rid of that by dividing by KEQ on both sides. So I divide by KEQ, that's gone. Now the KEQ is there. So that's going to be our setup. So let me go ahead and rewrite it. Fe is equal to iron 3 sulfate times hydrogen gas divided by sulfuric acid times the KEQ. Again, I move the Fe over here, KEQ there, so that way I can have it isolated since that's what we're looking for. From there, it's now substituting numbers in and we'll get our answer. So let's go ahead and do that. Fe equals, let's plug in the iron 3 sulfate, it is 2 molar, multiplied times hydrogen gas, which is 4 molar, divided by the concentration of sulfuric acid, which is 0.2 molar, times the KEQ. Alright, so that's going to give us the following answer. I'm going to go ahead and multiply numerators first. There's going to be 2 times 4, that's just an 8. And then denominator 133.3 times 0.2 gives me 26.66. I go ahead and divide that. So that's going to be 8 divided by that answer. It's going to go ahead and give me 0.30 molar. And that is our answer for the concentration of Fe. That takes care of example number 6. This also brings us to the end of our lesson and as well as the end of Unit 5. Thank you so much for watching.